All right, let's get right into it. Today, we're going to break down the absolute fundamentals of neural networks. And we're going to do it with a simple Q&A. I've got the questions, and I've got the answers. So let's start at the very beginning.
Okay, so let's just dive in. We hear the term neural networks thrown around everywhere these days. But how do they actually work? Like, what is the most basic, fundamental building block of the whole thing?
That is the perfect question, because it all comes down to the core unit, the neuron. We have to understand what that is first. So this core unit is called an artificial neuron, or sometimes you'll hear the term perceptron. And the whole idea is actually inspired by the biological neurons in our own brains. Its job is surprisingly simple. It just takes in a bunch of different pieces of information, does a really quick calculation, and then produces one single output.
Here's a super helpful way to think about it, especially if you've ever worked with databases. Just imagine a single neuron as one row in a table. That's it. It's basically a container for a specific set of values.
And what does it do? Well, it's an incredibly simple three-step process. First, it receives its inputs. Second, it computes something called a weighted sum of those inputs. And third, it produces an output. That's really all there is to it. Simple, right?
Okay, simple enough. But wait a minute. If it's just summing up some inputs, how does it think? How does it know that one piece of information is way more important than another?
Exactly. You've just hit on the most crucial point. Not all inputs are created equal. In any decision you make, some factors just matter more than others, right? A neural network needs a way to account for that.
And it does that with two key tools, weights and bias. Think of weights as just an importance score for each input. A higher weight means that input has more influence, more say, in the final output. The bias is kind of like a thumb on the scale. It's an adjustable constant that just helps the model fit the data a little bit better. So back to our database analogy, this is like running a calculation or a stored procedure on that single row of data to figure out its significance.
So the actual math happening inside that tiny neuron boils down to this really simple linear equation. You just multiply each input by its weight, you sum all of that up, and then you add the bias. That is literally how it prioritizes information. Okay, I'm with you. So the neuron calculates a number, but what happens next? How does that number turn into an actual decision or a final output?
That's the perfect question, because it brings us to the final and maybe the most critical step. The number from our little equation gets fed into something called an activation function. This function's job is to take that result and decide what the neuron's final output should be. It's what determines whether the neuron fires or stays quiet.
Sticking with our database analogy, an activation function is basically like a case statement or an if-then block in SQL. It looks at the calculated value and, based on a set of rules, decides what the final output for that row should be. Now, you might be thinking, why not just use a simple on-off switch, a step function? But it turns out that's just too abrupt. If a tiny little change in a weight causes a massive flip from off to on, the network can't learn effectively. It needs smoother, more nuanced functions that allow for gradual learning and adjustment.
That makes a lot of sense. So what do these smoother, more sophisticated decision-making functions actually look like in practice?
Let's take a quick look at three of the most common types. First, there's sigmoid. It creates this really nice, smooth S-curve, which is useful, but it can sometimes cause the network's learning to slow way down. Next up is relu, which is extremely popular because it's so simple and fast. Its one little drawback is that neurons can sometimes get stuck in the off position. And that's exactly why leaky relu was created. It's a small tweak designed to fix that dying relu problem.
But even with that potential issue, relu is pretty much the go-to default for most people. Why? Because its formula is just max of 0x. It's incredibly simple. That makes it computationally cheap, super fast, and surprisingly effective in a huge number of applications. Its simplicity is its real strength.
And of course, there are others. ELU, or exponential linear unit, can sometimes speed up learning even more. And then there's softmax, which is absolutely essential whenever you have a multi-class problem, like trying to decide if an image is a cat, a dog, or a bird. Softmax is brilliant because it outputs probabilities for each class that all add up to 1.
And there you have it. So if you're finding this explainer useful, please take a quick moment to hit that like button, share it with someone who might be interested, and definitely subscribe for more deep dives just like this one. All right, this has been a fantastic breakdown, but let's zoom out for a second. Why do these individual components, the neuron, the weights, the activation functions,
Why do they matter so much in the grand scheme of things?
Well, here's the crucial takeaway. Well, each individual part is incredibly simple. Their power comes from scale. Neurons, weights, and activation functions are just the fundamental building blocks. But when you layer thousands or even millions of them together, they create a network that can learn and recognize unbelievably complex patterns from data, patterns that no human could ever possibly program by hand.
Which leaves us with one final, pretty fascinating question to think about. If these are the simple, almost basic building blocks, what kind of complex thoughts can they ultimately build together?